right. No idea how this is going to work, but we will give it a shot. I'm going to talk, and we'll see if that's useful. All right, starting with the protocol here. Whoop. Okay. First thing we're building is a passive low-pass filter. So if you're unfamiliar with what that is, you can check out the information up here describing the frequency response and phase shift that we will expect to see, as well as kind of functionally what the design of low-pass filters are and how it works. So basically, there's a cutoff frequency which you get to that will allow certain frequencies up to that point to pass through, and then ones beyond that will be filtered out. Yep. You can kind of see that here in the plot, frequency shift. So the bandwidth is where you have an active region, basically, and the output begins to rapidly go to zero after a certain point, which you can actually see is where you have a the phase shift begins to trend back. So don't really know what else to say there. Okay. All right, so we got a 1 kilo ohm resistor and a 0.01 microfarad capacitor. Very simple circuit. We're going to be using the function generator to provide a input of 100 millivolts at a frequency of 5 kilohertz. So this is really simple, not complicated. Hopefully you can see that. So we're going to go ahead, put some wires to connect to. Probably going to randomly sing during all this also. So just be ready. All right, cool. Let's use black so it's easier to see. All right, so right now all we need is input, reference, and output. So we're going to get the splitter for our function generator, connect that there, run a reference signal over to the oscilloscope. Right. Power into the board using our mini grabbers. Obviously, we got our input, output, so power and ground, and we are, if you look at the diagram here, we're actually going to be connecting across the capacitor to measure V out. So we will do that with get ourselves a testing setup. All right, so now we're just going to measure. Look at that, already making mistakes. So if you look at the circuit diagram, you actually see that it's supposed to pass the resistor first, and then power goes through the capacitor. So, all right, got that. So connect this here. This actually will be funky. On top. Okay. So make sure everything is nice and connected to the board still. Cool. And yeah, so we're going to be using the tools here to power things and hopefully have a little clearer indication of what we're doing at each step. So All right, so we have done this. We've built the circuit. We have connected the output measurements. We are now displaying, yes, channel 2, channel 1. So when this says display the input signal, that's just your reference signal coming from your function generator. So we want that to be in channel 2. And the output signal to channel 1, that is our V out that we're measuring here. So set the input signal on the function generator to the following parameters: waveform, sinusoidal, VPP, 100 millivolts, frequency 5 kHz. Okay, we're going to go over here. We're going to go to our function generator. Sinusoidal, bam. 100 millivolt VPP, cool. Offset doesn't matter at this moment, so we're going to do 5 kilohertz. And yeah, we should be good to go ahead and turn output on. Okay, so we're going to go back here, and then if we want to look on the oscilloscope, we can see, let's go instrument settings. We want to actually auto scale this, because right now you can see this is a not super clean wave. So auto scale, and there we go. Cool. So let's see what we got. All right, so we're going to go ahead and use the measurement features to, we'll get VPP, V in and V out, and phase. So we want to be recording these. Let me see what we got here. So we don't need frequency. So let's go make a little table real quick. So we're going to need, we'll say that this is frequency. This is V in, V out. So we're starting with 5 kilohertz. Let's make it easier for plotting later. Let's just do units up here. And let's have these always be in volts. And this volts. All right, so we got 5 kilohertz. And if we go look, let's go ahead and make this all right now. We're going to be doing 10, 20, 30, 40, 50, blah, 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 up to 200. So starting with 5 kilohertz. So let's go ahead and do that. 10, 20, 30, 40, 50, 60, 70, 90, 100, and 200. The in should always be, we'll check as we go, but it should always be our 200 millivolt actual. So I guess we should put 0.2 millivolt actual input, since this is going to double coming out of the function generator. All right, so we got that. Let's go back over to here. So right now, if we, let's see, right here, measurements. We've got, so peak to peak for 1, this is our V out. It's equivalent pretty much to our V in. So we're going to put 0.2 volts there also. And I'm going to go ahead and put 0.2 for these. These should all be 0.2 volts. All right. We need to go ahead and add, so let's see, where do we go? Measure and setup. We want to do, that's not what we need, measurements. All right, so we want peak to peak 1. So we want to also have, where is it at? Phase. Somewhere. Sure, am I doing scope measurement type? Phase, bam. All right. All right. One thing to note when we're measuring phase, it has to be source 1 as your reference, because it's going to be comparing the phase between your 2 signals, and it always compares to 2. So if you're comparing 2 to 2, it's always going to be 0 because that's the exact same thing. So we're going to go phase comparing input 1 to input 2. Okay, so now we've got, gotta go and put VPP back on there. Peak, go 1, 2, and just so that we're sure, we'll add a signal measurement of frequency. Cool. We're going to resume here. So now got this all set up. Phase 1 to 2 is what we need to record also. This is just confirming that we have the frequency in, and so these should be all the inputs, measurements that we need. So phase 1 to 2 right now, it says to stop it. I guess we can go ahead and do that, see what it lands on. Okay, -15, that's pretty good. So we're gonna record that in our phase column, which I totally had before. So right now we're at -15. I believe this is technically degrees. Phase, and it is degrees. Cool. All right, so we got the 3 measurements it's asking us for. We'll go back, check that real quick. So we want to measure VP of V in, V out, and phase for the corresponding frequency. Looks good. All right, so now we just got to do that at 10 kilohertz, 20, and so forth. So we're done. So that's going to be kind of tedious, but not bad. So we're going to hop back over to the function generator. Yeah, just right here. Go 10, and now we're going to, again, we want to auto scale. If you don't have this auto scale correctly, the phase measurement is going to be, the accuracy will decrease as you get more and more waveforms in there. So we're going to stop it again, 26.72. We're going to do, all right, so peak 1 is now 180 millivolts, and phase is -26.8. We'll round it up. All right, and on to the next. So we're going to go back to 20 now. All right, run and auto scale. Isn't this exciting? All right, pause it. And we got 130 millivolts for our peak. And phase is -48.4. Alrighty. $30. Auto scale again. All right, so it's not wanting to auto scale any further in, it looks like. So at this point, we can either just go with what it has. If you wanted to, you could also adjust the controls to zoom in a little bit. Yeah, so it looks like you can't actually fit 2 full waves on there, so that's why they scaled like that. So that's fine, we'll leave it there. All right, so we'll pause it and record. This is going to be 55.2 for our phase. And let me go ahead before I forget and add this here, that this is the passive low pass filter. And we can make that nice and pretty if we want. Cool. So now we're on to 40 kilohertz input. All right. Pause that. And we're down to 80 millivolts. So it looks like you can kind of guess what we're going to see here when we end up plotting this. And let's go ahead, we'll go look real quick since we're about halfway through the measurements here. Let's pop back over here. And so basically we're looking at this waveform here, right? We're looking at this phase shift, and we are on this slope right here. And also, in a similar fashion, we're on this rapid decline of our magnitude of our output, right? So we're seeing it go from being like a 1-to-1 or a 0 decibel change to already we're down to 0.08, so like less than half of our reference signal. So just to kind of keep in mind on what the purpose of this is, the idea of what we're doing, we're basically reconstructing these with an actual circuit that we built, or I guess I built. So, okay, continuing on, we just did, what do we do? 40, so we're on to 50 kilohertz input. And on scale again. All right. So stop it. Actually, I'm gonna layer on. This is why the instructions say to pause it. If you can see here, the since we're getting it to such a high frequency, it's actually the ability of our oscilloscope to like accurately collect the waveform is not the best. So by pausing it, we actually ensure we just have a single wave going through there, and it's going to give us it's not like easier to read data at least. Hopefully, we stop it at an accurate time. So we're down to 70 millivolts with a phase of 70. We'll do 62,000 kilohertz. This is probably boring as all get out to watch. But hey, doing what we can. All right, run that, auto scale that. Go ahead and pause it, and well, yeah, this is how fast labs should go. Not pointing fingers at all. So that's 60,000 kilohertz, cool. So I'm gonna do 70. This interface, also the Keysight interface, I think is pretty useful when it's working. So if you or your partner does have the access that you need to get to use this, I know some people still can't get it to open correctly, but I think it does actually speed up the lab a little bit, and it lets you do change settings and stuff very quickly. So if you like using it, just feel free to do that during the class, if we ever have class again. Okay, so now we're down to 55. Don't judge me. And then phase is -69. Oh, that was supposed to be next. So, oh shit. All right. We're gonna go A. Okay. This is the, so you see it says overload. It is failing to give us, okay, there. So you just have to, I just had to keep trying to get it to pause to where it could actually see a full waveform and be able to tell us the measurement there. Cool. So we got down to there, and the okay. So you can see we're kind of plateauing here with our phase shift and voltage output. So unexpected not to change too much for the next two measurements either. That's why we have that big. So if you look, the last measurement goes up 100 kilohertz. That's just to basically skip to the bottom of this graph real quick. If we like over here. So yeah, okay, 90. And then back here, run, auto scale. Stop. All right, 39 millivolts with a phase shift of, that is 78. Now we're doing 100 kilohertz. Whoops. Kilohertz. Okay. And we will. So one thing to keep in mind as we're recording this and looking at those graphs, let me go ahead and record this real quick. So we got still about there, and negative 82. So just as a reminder, this is a logarithmic frequency scale. So initially when we're going 5, 10, 20, that is, we saw significant changes here because we were following this logarithmic trend. But once we started going up by 10 kilohertz, the difference between the measurement points became smaller and smaller and smaller, basically, which is why we stopped seeing such a strong shift here between the different points, just so you can understand why it does that. Okay. Yep. Let's go do, now we're on 200, and that's the last measurement for this part of the lab. Okay. That is a pretty signal. Okay, so now I'm going to have to basically play with this to get it to give us some sort of decent measurement. So I went to fine control. I'm going to shift this over a little bit. And, all right. So we're going to pause it, see if it gives us something. And we'll try it again. There we go. Okay. So yeah, this is like 200 kilohertz. That's pretty fast frequency. So oscilloscope has a little bit of a hard time measuring it as it's running. So that's why we pause it. All right, so we're down to 0.02 volts or 20 millivolt output and a phase shift of pretty close to negative 90. So, I stopped doing decimal points. Whatever. We'll run them all up. This is just for, again, we're just trying to get the trend here. Were we all to do this in class, it would be different numbers, but not different enough to change the actual graph at the end that we plot that has like the best fit curve and everything. So this looks good. This is, I think, a pretty good set of data. So if we wanted to compare to the actual chart here, it does. You see it kind of bottoms out at negative 90. You can see that we were reaching a plateau there. For the phase shift, frequency response is down to less than a tenth of what it was initially. So yeah, this is stuff you're going to have to convert this data into these plots and include that as the part of the report. But hopefully that you kind of understand what it is that we did, right? We ran through this frequency spread here. This, there's a word for it. That's fine. And got this output to, basically verify, in fact, that we did build a low-pass filter. All right. So on to the next part. We did all this. We did this for all of these frequencies. Tabularize all data. Hey, here's a pre-made table for you guys, including, did that. So just make a Bode magnitude plot and phase plot with this data. Just keep in mind that that should be in logarithmic scale. So if you have questions about how to do that, let me know. We can help you out, but give it a shot before coming to us, please. This is shouldn't be too hard. Okay. Next, we are. Y'all can do that. Did I answer this? All right. So, part 1C, on to the next one. Using the same circuits. Okay, so we need to basically adjust the frequency until the phase becomes 0. So actually, we know we're at 5 kilohertz. We were getting close. Thinking about this graph here, we're basically looking for this spot right here, right? Or sorry, on the phase chart. So we're looking at where as close as we can to where it is about 0 phase. 5 kilohertz input gave us maybe here. So I'm thinking maybe like 1 kilohertz is a good place to start. So we'll go over to our function generator. Let's try 1 kilohertz first and see what we get. We'll run that. And auto scale. All right, phase is -3, pretty close. Not quite 0, so we can back it off a little more. We'll just go back to, okay. So 1 kilohertz, we'll bump it down to, let's say 800 hertz. See what that gives us. Phase shift, let's auto scale it. Phase of, all right, don't like that. Okay. -1, -2-ish, right? Not quite 0. We're going to bump it down some more. So we'll go down to, let's say, 600. All right, auto scale again. Okay. So phase, I think this is about as close to 0 as we're going to get. Looking at this, so I'm going to pause it real quick. Yeah, so this is like basically 0. You can't, let me see if I can get one. Yeah, it's basically 0. It's having a really hard time even like measuring anything. It's easier to see on the actual piece of equipment because it's jumping around so fast. But we're going to call this good. So what does it want us to do? So it says, all right. Wait, part 1C becomes 0. So we're thinking that's about 600 hertz. Record all of this to freeze the signal, blah, blah, blah. Okay. So, all right, let's go ahead and, this isn't. We'll just keep it here. We'll say this is part 1. This is data for part 1B. And we'll say that we're doing phase shift. This is part 1C. So we're inputting phase now. starting with 0. Right, and we are measuring VPP of VN, so we're doing the same measurements basically. Keep that consistent. VN, V out, and frequency this time. So we're basically just doing this in a, rather than changing frequency and seeing the response, we're changing phase. Or I guess manipulating frequency to give us a desired phase and then reporting at what frequency that was. So just a different way to basically get the same data. Don't know how I feel about that. Okay, so right now we're seeing still a 200 millivolt. You know what? We'll just leave it in volts right now. Calculations won't change that. Sure. Okay, so V out is still 2 volts, 2 millivolts, 200 millivolts, whatever. Frequency 600. And this will be, actually, I think we're going to get up pretty high, so we'll say that it's 0.6 kilohertz. Okay. Make all this nice and pretty. Okay, so now we're going phase shifting. So, all right. Pull back up the protocol. We got -8/pi, which I'm going to convert to degrees because that's what we're actually going to be looking at. So that's -22.5 degrees. Pi, -pi/4 is going to be -45, -67.5 should be right. Add those two together. And then -90. Okay. So we're going to go ahead and jump over here. We want to now try to get, so we're trying to get to -22.5 degrees for our phase shift. Were you doing this? I don't know if I would have told you guys, but I'm going to go ahead and just look over here. We have phases that we know we got. So our frequency that we want is going to be between 5 and 10, right, to get a phase of -22.5. Thinking about this logically. I'm just going to go ahead and guess 8 kilohertz is going to be my guess. And we'll see what we get. So we'll hop over here and go 8 kilohertz and auto scale that. 23.4. That is close. Oh, that's close. We'll go 7.5 kilohertz. Try that. 21. Damn it. All right. We're gonna go. I think I'm just gonna leave it 8. That was pretty close. Again, we're trying to get the trends here, so look at that. Okay, that is well within reasonable distance from that. Okay, so we're gonna record these values. The in, as always, is 200 millivolts. Our output now is about 185, 190 millivolts. The frequency that we're doing this at is, 8 kilohertz. And now we're trying to get -45. So looking over here, that's almost exactly 20 kilohertz input. So we'll try 19 kilohertz. See if we like that. Jump back over here. Auto scale. And 47.5, a little high. That's gonna be close enough. Yeah, we're gonna call that close enough. So, all right. So we got -45. We got frequency. All right. So wait, V in 200 millivolts. V out is now 140. Frequency is 19 kilohertz. Cool beans. 67.5. We're going to drop off a few from 70. Nah, we want to be between these two, right? Yeah, so this was 65, this was 70. It's going to be probably close to halfway between these. We'll try, I'm going to say 48 because I feel like it. All right. Run that auto scale. We need 70, 67. Let's see what we got. That's good. All right, we will take that one. Okay, V out is now real low, about 70 millivolts. Frequency is 48. Yeah. Okay, these are good. And then we're going to do -90. We got close with 200. This is, again, a log scale. So I'm going to jump up. I'm just going to double this again and move, probably get pretty close to -90. So we're going to go 400 kilohertz. Wicked fast, as they say. All right, auto scale. Oh, yeah, that looks beautiful. All right, I want to back this off to about here. Okay, we'll pause it, see what we get. That looks like, okay, well, that's annoying. Oh, come on, this is, we're just playing games here. It is about -90. I needed to like, damn it. Oh, we saw it. You saw it there. Oh, come on. Whatever. That's close. Shit, that's close enough. We are taking it. Boo. Okay, so input, output is now down to 12.5 millivolts. So that's like nothing. And then frequency 400. That is cool. So that's all the data we needed for, I believe, for that part. Let's go check. Yeah. Okay. Cool. So we got the data here. I'm thinking that's going to look good. Plot it out. That's fine. Tabulate all data, frequency values, blah, 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 blah. Compare and discuss. All respective data sets for you guys. Okay. Design circuit. So hopefully you guys did this already. It's not complicated at all. Basically, we're doing the same thing, but with an op amp in there. So yeah, so we're going to go ahead and build that. So that's going to be sorry, we want to do those passive high pass filter. Sorry, it's not even active yet. Boring stuff. So we want a passive high pass. Okay, so we're switching from low pass to high pass. Yes, we're going to use these same materials here and build a passive high pass filter. Pro tip, that's just switching the capacitor and the resistor. So we could really just switch the inputs, I guess, like the probes, but we're not. I'm just gonna, for the sake of conceptualizing it, we're just gonna switch these guys here. All right. And again, we're still measuring. This time, actually, we're measuring across the resistor. So the second component in the circuit. All right, those both look good. Good, good. Okay, cool. Right, so we're going to go back to here. So our input's going to be sine wave again, 100 millivolt PPP, frequency 5 kilohertz. All right, so same as last time when we started. So we're going to go to our function generator. And we're still here. And so we got sine wave, 100 millivolts, frequency 5 kilohertz. All right, run auto scale. That's not right. Okay, well, it's being weird, so I'm manually adjusting it since it won't auto scale correctly. All right, so this looks good. Cool. So it wants us to, press auto scale until it doesn't work. Then you got to do it by hand, but we're good. Measurement features, so VPP, VN, so the same stuff as before. We're just doing this. So basically repeating what we did last time with a, exactly, I guess. So I'm just gonna do that, and we'll just go down here. And now we're doing a high pass filter. So this is part 1D, right? Yeah, okay. Same input. So V out and phase are going to be different. I regret putting it in volts, so we're going to go ahead and do millivolts this time. And we're going to pretend that it's not going to change the the math will work out the same since we're basically measuring the shift between these two. It's mathematically the same, but I'll feel better being able to type out the whole numbers, I guess. All right, so we got 200 millivolt input. We got 5 kilohertz. Output 66 millivolts. Phase is 70, 75-ish. We'll pause and see what we get. 76. Sure. I'm gonna put 75. It was bouncing around there, and it seemed to be the median. All right. So on to 10. This is gotta be so boring to watch. I am sorry you guys aren't here doing this. All right, auto scale. Actually looks decent. Pause that. And now we got 11. We got 62-ish. Sure. All right. I'm gonna switch up. We don't need that. We don't need that. Why is it not letting me? Dumb. Okay. All right. This is, it doesn't look great. Whatever. Okay. So we're going to go to here. We're going 20 kilohertz now. We're going to, I wish I could have it side by side. That's just ugly as hell. Okay. That's fine. So we'll run that. And we are on 20, right? Yeah. So we'll auto scale. I'll let it run for a sec. Pause it. All right. So now we got 1 millivolts. Output, we got phase shift 39.9, so 40. All right. So now we're doing 30. And that's going to be 169 and 30 for our phase. 40. That seems faster, right? We're booking it. Watch this at like 1.5 speed or something. All right, 181, 25 for our phase. Also, well, you know what? I'll let you guys think about that. These values that we're getting. Okay. 50. Run, auto scale, and stop. Peak is still 181. All right. Phase 22. 60, run. $189. 16.8. Where's 17? 70. I don't really even know what to talk about during this. This is just tedious research, kind of. Not really. Kind of like research. Okay, 197. So we're basically back to having like a magnitude change of 0. And our phase is down to 15. All right. 80. Run. All right. That looks fine. Yeah, so we're basically plateauing here. And this is 14. 90. Run. I'm going to bump this one. Pause. We got 12.3, 189. Yeah. Again, this is a logarithmic change we see as we go through these frequencies. So we're basically like petering out the difference we're going to see between each of these measurements. 100. Run. Stop. All right. 200. Hopefully see a nice shift here. All right. Yeah, so we go down to 8 for the phase. Okay, cool. So we got all that. Woo, exciting. All right. Done here. We tabulate all the data. We have the values we need. You're making another magnitude and phase plot. So yeah, you can see this is basically like, opposite response of this, right? So at low frequencies, we are, it's filtering out those signals. Whereas when we get up to 100, 200 kilohertz, we're seeing almost the phase shift is negligible, and we're getting a almost 1-to-1 output for our V out. So, okay. All right, done that. Done. All right, so that's part 1. Bam. So we're on to part 2. Cool beans. Let's go. So we need a 1 kilo ohm resistor. We got that. We got a 4.7. Blah, 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 blah. Okay. Measure and record the resistance values. I didn't do that before. And we'll do that now, I guess. It's going to be, we're using the same 1 kilo ohm resistor, so we're just going to do that. All right. Disconnect these guys real quick. For everyone to be able to see. I'll do it on here. So we're going to go ahead and open up the multimeter. So we want to measure resistance. Okay, that's interesting. All right, cool. Guess that doesn't work. We're gonna just do it on here. Local 2 watt. Yeah. All right. So don't know if I can see.